What you see here is a function called primes, which selects from a handful of numbers those which are prime numbers. And when you have a look at this code, you might say, yeah, this looks pretty easy to understand. Now, this might be just one function in your large code base, and you would like to know if there are any other functions in your code which are a bit harder to understand. As developers, we spend a lot of time on understanding source code, so that optimizations here and there would certainly be a good idea to save some time in the future. And this is where metrics come into play. A metric that calculates the understandability of our example here could come to the conclusion, easy to understand. This video is about such a metric. It's called cognitive complexity, has been developed only 3 years ago and claims to measure source code understandability. Instead of easy to understand, the metric calculates a number. 3 in this case. In very simple terms, every time there is a for loop or an if statement or other interruptions in the linear control flow, a counter is incremented. So +1 for this for loop here, and +1 for this if statement over there. At the same time, the increment depends on the nesting level. Our if statement is within the for loop. This is why we increment here by 2 instead of 1. Intuitively, this makes sense. The more we break out of the linear flow and the deeper we nest our code, the more cognitive load one would expect and the more difficult the code is to understand. Now, the issue is that, in this case, it is the same as with most metrics reported by code analysis tools today. They have not been validated yet. In other words, many metrics claim to measure specific quality attributes but have never been shown to do so. This is why we took cognitive complexity as a metric and did some research. Will this be the first validated metric that can automatically measure code understandability? Let's find it out. An empirical validation of cognitive complexity as a measure of source code understandability. That's the title of our paper, which was recently accepted at a conference called Empirical Software Engineering and Measurement. Empirical software engineering is a very exciting field in which a lot of different research is published. What these studies have in common is that they aim to better understand software engineering by collecting and analyzing data. In this work, we have collected data to validate whether the cognitive complexity metric actually reflects how well developers can understand source code. An obvious study design would be to invite, for example, 50 people and watch them understand some code snippets. But then we would have ended up with exactly that, 50 people and information on a handful of code snippets. Would that be enough data to say something about how well the metric works? Probably not. So instead, we went looking for the datasets of existing studies on code comprehension. Let me give you an example. There's this study called Shorter Identifiers Take Longer to Comprehend. It's a nice study. They told 72 participants to find a defect in a code snippet and measure the time it took them to find the defect. Spoiler alert, the result is that shorter identifiers take longer to comprehend. While this is a cool result, we were more interested in the dataset of the study because this would tell us for the investigated code snippets of this study how well developers understood them. Now you might already see where this is going. Taking these data, we could calculate the cognitive complexity value for each code snippet ourselves and see if it correlates with the measured understanding. For example, for code snippet A, it took participants in this study 76 seconds on average to understand the snippet, and the cognitive complexity of the snippet is a 5. Snippet B took them almost 2 minutes to understand, and the cognitive complexity might be a 10. And we can find out how well the metric and the understanding measurements go together by calculating a correlation coefficient. At this point, we calculated exactly one correlation value that indicates how well the metric works on the dataset of this one study. And now let me tell you that this is not the only study on code comprehension out there, so we went to find them all in a systematic literature search. We described the literature search in great detail in our paper, and I've linked the paper in the video description. What we basically did was to search for all studies that measured the understandability of code snippets as part of their study with human participants. Starting with 7,000 initial search results, we ended up with 56 papers that met our inclusion criteria. Of these, slightly less than half had published not only their paper, but also their dataset. And finally, of these datasets, 10 were of a format that allowed us to work with them. So we had a total of 10 datasets in the end to work with. Speaking in numbers, we ended up with a total of 427 code snippets with about 24,000 evaluations. Enough data to investigate whether these evaluations correlate with the cognitive complexity metric, and definitely more than we would have obtained ourselves in a single study. Before I present the results, two things are important. First, the construct of code understandability is measured in several different ways. Some studies measure the time it takes developers to understand the code snippets. Others measure the correctness of answers to comprehension questions, and still others simply let developers give their subjective rating of the code understandability. So far, we don't know how these measures are related, and therefore reported the results grouped by each measure. We will shortly see what this means. Second, the actual analysis method can be summarized as meta-analysis using the random effects model. This sounds complicated, but can be explained in very simple terms using the concrete results. Here we go. These 9 studies here measured the time it took participants to understand specific code snippets. Right in the column next to it, we see the number of code snippets that were evaluated in each study. This has a small influence on the weighting of the respective study for the final result. For each study, we calculated a correlation coefficient. This coefficient indicates how well the values of the cognitive complexity metric correlate with the measured times it took developers to understand code. The correlation value is always in the range from -1 to 1. In this case, we expect a positive correlation, because if the code is difficult to understand according to the metric, then we expect that developers also need more time to understand the code. Accordingly, each correlation value greater than 0 supports the assumption that the metric works well. Now, look at this. We already see a clear tendency towards positive values here. The 9 correlation coefficients are then combined into a single value using the random effects model. This is basically a weighted mean of the 9 correlation coefficients, which is more meaningful than any single correlation coefficient, since the data of all 9 studies are considered. 0.54 is a large positive correlation and supports the idea that the values of the cognitive complexity metric are a good indicator of how long it takes developers to understand code snippets. This is already a pretty good result, since time is something we all have too little of. We did such an analysis also for measures of correctness, subjective ratings, physiological variables, and the combination of time and correctness. Our results were highly positive for time, as we have just seen, but also for subjective ratings and the combination of time and correctness. We observed mixed results for correctness and physiological variables, but to a neutral extent. This can have several reasons, and we refer to a discussion on this in our paper. To the evaluation of the physiological variables, we must add that our results are based on the dataset of a single study. This study measured code understanding in an fMRI scanner. The results for correctness also showed a tendency to support the metric, but in the end only a weak correlation was calculated. All in all, the cognitive complexity metric works very well, and we can now claim, for all we know, that it is the first validated metric that can actually measure code understandability. If you calculate the metric on your code, for example by using the static code analysis tool SonarQube, our recommendation is to keep the metric value as low as possible. Finally, 2 comments. First, a word to all scientists who feel at home in empirical software engineering. Please publish not only your paper, but also your data. I know that this can be time-consuming for so many reasons, but let me tell you that there are people out there who will be grateful to you one day. And nope, providing data on request is not a long-term solution. We asked 12 authors whose study would have been relevant for our purposes whether they could provide us with their data. Only 6 of them answered us, and only 3 of them could offer us their dataset. Whenever possible, try to make your data available. And last but not least, if you liked this video, you might want to subscribe to /science. It's a new YouTube channel where I plan to communicate scientific findings in software engineering in a way that is not only understandable for scientists. I'm super happy about any support. My name is Marvin Wierich. Thanks and see you soon.